Hello friends, I am Rahul and you are watching Truth of Physics. Today I will discuss the one-dimensional Dirac delta function. Previously I have made a video on the topic the introduction to Dirac delta function. In that video I have covered the concept behind the Dirac delta function, that is why the Dirac delta function is necessary, and in that video I have also discussed a very fundamental problem of electrostatics, and I have also said that the problem can only be solved with the help of this Dirac delta function. So in this video I will describe detailedly the one-dimensional Dirac delta function, and all the concepts I will clear in this video, and in the next videos, upcoming videos, I will also clear the topic the three-dimensional Dirac delta function, and then you will also understand the how the Dirac delta function can be used in that particular problem which I have covered, which I have discussed in the first video. So if you have not watched the first video, then I will give the videos link in the description box. You can watch, and you can watch that video also. Dirac delta function is described or is defined like this way. We have a function like this, del of x, which defines or which represents the Dirac delta function. Del of x is equal to 0 at any value of x except at x equals to 0, and its value is infinity at x equals to 0. So think about it. Just this will look like this. This graph with this graph is the graph of this function, okay, the Dirac delta function. So at x equals to 0, this tends to infinity, the functional value y, and at any point except x equals to 0, as we move forward in the x direction or as we move in the negative x direction, the value is 0. So this is what? This is a type of infinite, right? Infinite spike, right? Infinite needle or infinite spike, this type of function. So okay, now this is defined mathematically. Now let us understand this Dirac delta function with a simple example. Let us we have a sequence of functions like this. We have a sequence of functions like this. We have a sequence of rectangles, okay, and the rectangles are such: n equals to its n is its height, and 1 by n is its base. Okay, we have such type of rectangles. So as we put the values of n, any values of n, like 1 2 3 4, then we will get 1 by 2 comma 2, 1 by 3 comma 3, 1 by 4 comma 4, this type of rectangles, right? This is the base and this is the height. This is the base and this is the height. This is the base and this is the height. So these rectangles will be like this. Suppose the rectangles will be like this. So as we move towards infinity, as n tends to infinity, then think about what will be the situation. Then as n tends to infinity, then height tends to infinity and base tends to 0. Okay, then the base will be tends to 0. So think about that condition at when nearly equals to infinity, n is nearly equals to infinity at that region, then this will be purely a spike, right? Purely a infinite spike whose base is 1 by n and height is obviously n. So think about that. Other than at x equals to 0, this is at x equals to 0, then other than the point x equals to 0, the functional value, that is y, that is the height of that rectangle, is 0 except at x equals to 0, and at x equals to 0, this is the height is infinity. So this will turn into our Dirac delta function, that is this will turn into this, the Dirac delta function. So here del of x, we can write this function like this. This is a Dirac delta function where del of x is equals to 0 and infinity 0 when at x not equals to 0 and infinity at x equals to 0. Now one more important thing. Suppose we want to find the area, then you can understand easily that each of these rectangles have area what? Each of these rectangles have area n into 1 by n, that is n into 1 by n, that is 1. So this will be applied for each and every rectangle. That is when the case appears that n tends to infinity, then also this is valid, then also the area of the rectangle will be 1. Each and every rectangles have area 1. Then and calculus, in the language of calculus, how we can define the area? We can define the area like in integration, in the sign of integration. So we have integration over del x dx. Del x means what? Del x means nothing but this function, right? This function is represented in the Dirac delta function, and why we have discussed this previously, that this function is turned into the Dirac delta function. So these conditions will be applied here also. So when we integrate del x dx over the range minus infinity to plus infinity, okay, over the range minus infinity to plus infinity, that is over all the range, right, minus infinity to plus infinity, then what we will get? We will get nothing but the area of the curve under the curve, right? That is, we will get this area, the area of that Dirac delta function, and that is what? That is 1. This is a very important result. This is a very important result. So how this result come? We have understood this with the help of this very simple example of rectangles. Okay, so we have two fundamental properties of Dirac delta function, that is, one is this and second is this. Now we will understand some more fundamental properties of Dirac delta function. Suppose we have a arbitrary function f of x. So del x into f of x, I can write this like this. This will be equals to del x into f of 0, which is also equals to del x into f of 1. Now you can have a question that why I have written this. The simple reason is behind this, when we put the value of x except at x equals to 0, when we put x equals to 1, x equals to 2, x equals to 3, then what will be this product? Del x into f of x. This will be nothing but this will be equals to 0, because del of x is equals to 0 at any point except at x equals to 0. So the product will also be equals to 0 except at x equals to 0. So these all have same significances. These all have same significances. Or if we write del x into f of 2, del x into f of 3, all these have same significances and same value also, because all these have values at x equals to 0, infinity, and at x equals to s not equal at x equals to 0, this is x equals to 0, and at x not equals to 0, this product will result 0, right? So this is the reason why I have write like this. Now one more thing, what will be the value of this minus infinity to infinity del of x into f of x? Now what will be this? So we can write, okay, there will be a dx. So this will be equals to, I can write this like this. So if we put this here, so this will be now f of 0 can be taken outside of the integral because it is a constant. F of 0 is the functional value of at x equals to 0 of that function, right? So this will be taken outside of the integral, and the integral will be del x into dx. Now previously I have discussed that this integral is nothing but is equals to 1. So this will be f of 0 because this is 1. Okay, this is 1. So what we have into f of x. So this is a very important property of Dirac delta function. What it tells about? It tells us that when suppose we have a function f of x and we want to find the functional value f of x at x equals to 0, that is we want to find f of 0. So if we calculate this, if we multiply the function with the Dirac delta function and take its integral over minus infinity to plus infinity, then we will get f of 0. That is, this expression or this expression will take, that is this expression dx, here dx, this expression is taking or putting out the value of that function f, of that functional value of x at x equals to 0. This is the use and this is the benefit of the Dirac delta function. Now how we will find f of 2, f of 3, f of 4 and any value of the function, how can we find like this way? Let us understand it. Now first we will understand del of x minus a. Like any function like f of x, suppose we have a function f of x like this is y equals to x, right? We have a function y equals to x. So this graph will be like this, a straight line passing through the origin y equals to x. Now if we make the function y equals to x minus a, that is f of x is equals to x minus a, then what will be happen here? Then the graph of this function will be shifted rightward. As we as we are subtracting x minus a, then the graph will be shifted rightward. At what length? At the length of a, right? So this can be understood very easily. Now I will put this concept here. Now del of x minus a will also shift the previous Dirac delta function, that is the Dirac delta function del of x, to rightward direction. At what amount? At amount a, that is this length will be a. Now this is x equals to a. The Dirac delta function is shifted rightward with the value of x equals to a. Okay, now this will be 0 and infinity at what point? You have to understand that this value will be 0 at x equals to 0, x not equals to a, and this will be infinity at x equals to a. Okay, it is clear now. Now what will happen when we calculate del of x minus a into f of x, integration minus infinity to plus infinity into dx? What we will get? Similarly, like this, we will get here the functional value f of a, because now all conditions are shifted rightward, or the function is shifted rightward at x equals to a. So you have understood very clearly that this will be happened here now. So like this way we can find any value of f, that is any value of the function, like this way. Okay, now the one more thing is that the limit, that is here it is not necessary that the limit has to be from minus infinity to plus infinity. That is, if we have the limit like this, minus a by 2 to minus a by 2 is here, minus a by 2, and there the upper limit is suppose 3a by 2, 3a by 2, and del of x minus a into f of x is also equals to then f of a. That is, there also then also the condition is valid for this limit. So why this is happening? Because we can understand that when the limit was from minus infinity to plus infinity, then for the range except this range, except at x equals to a, the other range in all the other ranges, that is in all the other points except at x equals to a, the condition is null. That is, the product will be null because the Dirac delta function is 0 at any other point. So all the contribution is coming from this region, right, from x equals to a. So we have to limit, we have to give the limit to cover only the Dirac delta function. This has to be our main aim. Okay, we have to cover this Dirac delta function region. Right, that is, we have to cover where the Dirac delta function is tending to infinity, that is at x equals to a. And when we cover this in the limit from minus a by 2 to plus 3a by 2, then the infinity range is covered, so the condition is valid. Likewise, this limit can also be from x equals to 0 to x equals to 10a, right? Ax minus a into f of x. All the vicinity points can be applied here as limit. Okay, but you have to concern that this region is covered in that limit. Okay, so this is all the concepts and all the formulas and all the properties of Dirac delta function. So I think that you have understand all the concepts behind this topic, the Dirac delta function, one-dimensional Dirac delta function. In the next video, I will describe and detailedly discuss on the topic three-dimensional Dirac delta function, and I will also cover that how the problem which I have mentioned in the first video of the Dirac delta function, how the problem can be solved with the help of three-dimensional Dirac delta function or Dirac delta function. How the problem can be solved easily with the help of Dirac delta function. So stay tuned and subscribe this channel if you are new to this channel for the latest notifications of the upcoming videos. So take care of yourself. Thank you for watching.